Hello and good morning and welcome you all for this class on economic dispatch of thermal units. In the previous class we have learnt about a very important programming approach, optimization technique, which is dynamic programming, with the help of which we could able to solve the power system optimization problem very easily. We have taken some examples while we explained two different types of dynamic programming techniques, which is reverse or forward recursive algorithm and backward recursive algorithm or approach, FRA, forward recursive approach, and backward recursive approach. So we discussed about three different terms, which is stages and states as well as policies. So we divide the problem. Let's say you need to move from a destination source to a destination, and then we divide it into different stages, and we keep on finding an optimal state in the case of forward recursive approach, moving forward from the source to the destination. So at every stage we will find out that optimal state, and then we will move to the next stage, and then we will ultimately get the sub policies, combining which will get the overall policy, which is the most optimal one. Whereas in the case of backward recursive algorithm or approach, we start from the destination side and moving towards the source side, and we get the optimal states of the future state when we come to the previous stage, right? So both the techniques have its own advantage, and moreover the backward recursive approach seems to be more efficient and easy as compared to the forward recursive approach. Now in today's discussion we will learn about very important subject matter, which is known as economic dispatch of thermal units. See, economic dispatch problem without considering the transmission line effects. First we will deal about economic dispatch problem without considering transmission line effects. Let's say there are n generators. Which are connected to the bus bar. I hope you are very much familiar with what do you mean by bus bar. There is a bus to which you connect the lines, as well as there could be some loads which are connected to this buses. So, and to this bus bar there are n generators which are connected. You can see also in the picture that there is a fuel inputs and there is a boiler. So there is fuel input to each boiler. This is a thermal power system network, and the boiler which will convert the fuel could be a coal or could be oil, whatever it could be, and then from this it will convert it into supersaturated steam, right? So fuel input is in terms of chemical energy, and output you will get the heat energy, and that can be transformed into mechanical energy when you apply this to turbines. When these turbines are connected to their respective generators, and the generator output would be electrical. So the input is chemical to heat, chemical to, and then from heat to mechanical, and from mechanical to electrical. This is how a typical thermal power plant energy conversion takes place, from one form of energy to another form of energy, right? And the individual generator output, let's say for the first generator we call it as G1 and its output is P1. Similarly for generator 2 it's G2 and its output is P2, and similarly generator 3 its output is if this is Pn and its output is generator output is Pn, where the generator is called as Gn. So all these outputs are connected to one bus here. It looks like this. Similarly there could be different buses also for individual generator as well, and for this particular bus there is a load which is also connected, right? So multiple generator outputs which are synchronized together and connected to a common bus, and the output of all these generators, three things are common, which is voltage, frequency and phase angle. Then only you can able to synchronize, right? Now input to each unit is Fi, that is cost rate of fuel consumed, right? So the input is expressed in terms of chemical energy, and it has its own cost. Thermal unit has its own cost, where the cost is due to the coal, and output of each unit is PA and electrical power is generated. Essential operating constraint is that the sum of output power should be equal to the load demand, neglecting the losses. That means the power output P1 plus P2 up to Pn should be equal to P load. This is a constraint. Why this is constraint is there? Because if this generation output is not, let's say total P gen summation of I to n, this output is not equal to P load, then important parameter, that is frequency, gets disturbed. The frequency gets varied and it should be fixed for a safe and constant stable operation of a system, which is 50 hertz, right. So we need to maintain P generation is equal to P load, and economic dispatch problem is essentially the determination of the generation levels such that the total cost of generation FT becomes minimum for a defined load. For you can achieve summation of P gen is equal to P load with any combination of generations, but the objective of economic dispatch problem is to find out that particular combination of generators output, so that not only you may meet P gen is equal to P load, rather you will also achieve an important objective function, which is cost minimization. Now economic dispatch with different generating plants. So as we have come across in the first week, there are three different, typically nuclear power plants, hydro power plants and thermal power plants, right. In the case of nuclear power plants, they have little scope for the load variation because it is very complex to control the nuclear power plant. So what we do is we give a base load, whatever the load profile is there, load curve is there. So we will give the base load which is constant for the nuclear power plant. This is for nuclear. And hydro power plant, you can vary the power output based on the hydro input, and thermal power plant can be, the power output can be varied with the help of variation of coal. Now operating cost of hydro power plants do not change much with respect to the output, right, till the rated capacity, and we have learnt about also the characteristic curve. The information regarding the variation of the fuel cost rates for the fossil fuel based plants are crucial for formulating the ED problem. Ultimately it would be ED problem will be thermal plus hydro, how optimally utilize you thermal and hydro such that you will meet out the generation, sum of the generation is equal to load with the minimum cost of operation. Now generally the cost of labor, supply and maintenance would be fixed. Now this is a typical characteristics, nonlinear cost function characteristic of a thermal power plant. You see this is P minimum, this is P maximum. Between P minimum to P maximum the characteristic curve is non-linear. Let us say it can be expressed as AP square plus BP plus C. That means the input or fuel input depends upon, it's a characteristic function and it depends upon the output power, and it has its own non-linear behavior. That means if you increase the power output, then there is not linear increase in the power fuel input, it is a non-linear increase in the fuel input, right. So P minimum is the minimum output power level at which it is uneconomical or technically not feasible to operate the limit. Below this limit it is unviable technically and commercially also to operate a typical thermal power plant, and above P maximum there is a threshold to which it can generate. There is a thermal threshold for a power plant. Now the problem formulation is the objective function, as I already told, this is the total fuel cost. This includes the fuel cost of first generator, fuel cost of second generator and the fuel cost up to the fuel cost of the nth generator. So total fuel cost of all the generators put together is expressed as summation of I is equal to 1 to n and Fi of Pi, right. And what is the constraint? The total load, P load is equal to total generation, or the difference between load, total load and total generation should be 0, right. What is the inequality constraint? So we have learnt in our optimization preliminary understanding that there will be two types of constraints, one is equality constraint and inequality constraint. Equality constraint is summation of generation is equal to load. Inequality constraint here is the generation of each thermal power plant generator should be within this range, Pi minimum to Pi maximum. The reason I have already told that means below which it is unviable to operate economically, and above which there is a thermal capacity, because the conductor size has certain restriction. So beyond which there is a overheating that happens, and the generator may get short circuit or it may get burnt, right. So where n is the number of participating generators, this is a constrained optimization problem. We have learned there are two types of optimization problem. One is unconstrained, where we learnt about single variable and multivariable, and constrained, which has only equality constraint and equality plus inequality constraints. This is a constrained optimization problem. Now how do you find the solution? As we have already learned, we will find the solution by using the Lagrangian function. You see, this problem can be easily solved by using Lagrangian multiplier method. And what is a Lagrangian function? Lagrangian function is the fuel cost, total fuel cost, that is the objective function which you need to minimize, plus the Lagrangian multiplier lambda multiplied by the constraint, right, where the constraint is P load plus P loss minus summation of generation is equal to 0, and that should be your constraint. Accounts for the equality constraints, right, and lambda is a Lagrangian multiplier. Then what is the necessary condition? The derivative of Lagrangian function with respect to each independent variable is 0, right. That means this is your Lagrangian function, dou L by partial derivative of Lagrangian function with respect to each generator, dou L by dou Pi is equal to dou by dou Pi of this total function, which is, this is objective function and this is a constraint function multiplied by the Lagrangian multiplier. That will give you dou Fi by dou Pi minus lambda. If you can derive this, so let us say I am doing it for the first generator, right. So what do you get? Dou F by partial derivative of that function is only dou P1, because rest of the for the rest of the generators the partial derivative will come out to be 0, because other functions would be constant. So dou F by dou P1 minus the total generation, this is P load is a constant anyway, and minus, let us say you will get P1 plus P2 up to Pn, and dou P1 by dou P1 will give you 1, that multiplied by lambda you will get just lambda. So similarly for the second generator you will get dou F, this is dou F1, this is dou F2 by dou P2 minus lambda, right, and all of them will be is equal to 0, right, and dou L by dou lambda is equal to 5. This is for the generators. Again you will do the partial differential equation for the Lagrangian function with respect to the lambda, and that will come out to be the constraint function, that is it. Thus, to have the minimum fuel cost, the necessary condition is that the incremental fuel cost of all the generator should be same and is nothing but the Lagrangian multiplier, right. So whatever may be the number of generators, this holds good, that means dou F1 by dou P1 is equal to dou F2 by dou P2, similarly up to dou Fn by dou Pn is equal to lambda, right. Of course in this case we are ignoring the losses, we are considering that losses are ignored. Now to summarize, we have economic dispatch, following set of equations need to be satisfied. Dou F by dou Pi is equal to lambda, and this is the constraint, Pi minimum, the generation should be within the range of Pi minimum and Pi maximum for all the generators, and summation of generation is equal to load, and this note, whatever I have mentioned in the note now, this is very important. That means within this range of Pi minimum to Pi maximum, the dou F by dou Pi is equal to lambda for all the generators, right. Let us say if one of the generator touches either of the limits, if Pi is Pi minimum, then dou F by dou Pi is greater than or equal to lambda, right, and if Pi is equal to Pi maximum, if it touches the upper threshold, then the dou F by dou Pi should be less than or equal to lambda, right. These are the three observations that you will make when you solve a problem. This is your function, the characteristic function of a typical thermal power plant. AI Pi square plus Bi Pi plus Ci is equal to Fi of Pi. Now if you do the partial differential equation, then you will get Pi is equal to lambda minus Bi by 2Ai, and recalling the equality constraints, summation of generation is equal to load, then your Pi is nothing but lambda minus Bi by 2Ai, right, and that is equal to P load. Then if you solve, lambda you will get as P load plus summation of I is equal to 1 to n Bi by 2Ai divided by summation of I is equal to 1 to n 1 by 2Ai. Now we will take a problem to help understand this approach, Lagrangian multiplier based economic dispatch approach. Now the question is, determine the economic operating point for the 3 generating units when delivering a total load of 850 megawatt. Now the total load is given as 850 megawatt, and the characteristic function, the heat characteristic function of each coal fired steam unit is been given, and they have their own unique ABC coefficients, right. Now the fuel cost is also given, which is $1.1 per mega British thermal unit, and oil is $1 per MBTU. Now you need to have the fuel cost, total fuel cost, that is the generation characteristics multiplied by their fuel cost. You see here, first one is coal fired steam unit, and next two are oil fired. For the first characteristic function you multiply by 1.1, and for the second and third you multiply with 1, and then you will get fuel characteristic curve for each plant, each unit. Now you obtain the partial differential equation, that means you find dou F1 by dou P1 for each of them, and that should be is equal to your Lagrangian multiplier. And what is the constraint? P1 plus P2 plus P3 is equal to 850. Now you solve for lambda, that means you, from this expression you get to know what is P1, that is lambda minus 7.92 by this constant. Similarly for you replace for P2, replace for P3, then you will get what is lambda, right. Once you get the lambda, then you can easily find out what is P1. Go back and find out with this expression, you have got the lambda, you can obtain what is P1, P2 and P3 with the lambda that you have already solved, right. Now the combination of this P1, P2, P3 will be is equal to P load, right. That means in order to operate this thermal power plant, the combination of the thermal power plant fired by coal as well as oils, what is the most economical combination of generations? For generation 1 it is 393.2, for generation 2 it is, for second generator it is 334.6, for the third generator it is 122.2 megawatts. And let us take another example. Now determine the economic operating point for the 3 generating units when delivering a total of 850 megawatt. The same thing, but here there is a inequality constraints which has been added. Earlier there was only equality constraint. Now we are also increasing complexity to the next level. We are adding inequality constraint. Now coal price is changed and oil price remains the same. The same approach, obtain the fuel characteristics for each unit, then obtain the partial differential equation df1 by dp1 and df2 by dp2 and df3 by dp3, and they should be equal to the Lagrangian multiplier, which is lambda, and summation of generation should be equal to 850. Now this will give you lambda as 8.28, right. Obtain P1, P2, P3 just like the similar example, but you see here in the earlier case there was no inequality constraint. You need not have to worry whether each generation output for this economical operation have touched their lower or upper threshold or not. You need not have to worry that. But in this case there is inequality constraint which is already been mentioned in the question itself. So check for each unit whether any one of them are violating any constraint or not. Now the first generation power output is 703.125 megawatt, right, with this limit. The upper limit is 600 megawatt. So that means it is violating, correct. So and for unit 3 also, early the calculated value suggests it should be 32.157 megawatt, but if you can see here in the problem statement, it is given as the lower limit is of 50 megawatt. Now what to do? Let unit 1 be set to its maximum output. That means the Lagrangian multiplier based approach is suggesting increased generation of 1 as much as possible, right. So we now the maximum limit is 600. Now you fixed the generation of power, the power generation of the first unit to be as 600 megawatt, and limit the third generation to 50 megawatt, and you will get the immediate value of the second generation. It should be 200 megawatt, because P1 P2 is equal to 850 minus P1 minus P3, right. So you will get 200 megawatt. Since unit 2 is the only unit not at either limit, lambda must equal the incremental cost of unit 2, right. So what is lambda? Dou F2 by dF2 by dP2, and then you will get what is lambda, because you already fixed P1 and P3 and they cannot be equal to lambda. If they can be equal to lambda, then you should take the previous value, and that will violate the inequality constraint of generator 1 and generator 3. Now you will get lambda to be of 8.626. Now you have to check the partial differential equation, obtain the partial differential equation dF1 by dP1 when P1 is equal to 600. When Pn is equal to 600, what is the lambda that you are getting? 8.016, which is less than lambda. Similarly, obtain partial differential equation of fuel characteristics of generator 3 with respect to its generation, then you will get which is at 50 megawatt, then you will get 8.452, which is also coming out to be less than lambda. But if you remember the note, within the limit of generation, the partial differential equation of any generator should be equal to lambda. If it touches the upper threshold, then whatever lambda you get, whatever the value you get, that should be less than the lambda. And if it touches the lower threshold, then it should be greater than lambda. That means dF3 by dP3, as it touches the lower threshold, this should have been greater than lambda, and that lambda is obtained by that generator which is not violating the any constraint, inequality constraint. Here this is agreeing the dF2 by dP2, sorry, there is a mistake here, this is dF2. This is dF2, this is not dF1, this is dF2 by this is dF1 itself, this is dF1 itself, yeah, here dF2 by dP2, that is your generator which is not violating any constraint, and that comes out to be 8.626. Then you obtain for dF1 by dP1, and this generator is violating and it is touching the upper threshold. For that you are getting 8.016, which is less than lambda. That means this is in agreeable with the maximum constraint. dF1 by dP1 is less than lambda, this is fine. Whereas dF3 by dP3, which is greater than lambda, it should have been greater than lambda, but it is coming out to be 8.452, and this is still lesser than lambda. Then that means what it is indicating, incremental cost for unit 1 is less than lambda, indicating that it is at its maximum, but the incremental cost for unit 3 is not greater than lambda, so it should not be forced to its minimum. Then what we are going to do now is take up fix generator 1, P1 is equal to 600. Now you optimize for generation 2 and generation 3. So P1 plus P2 plus P3 is equal to 850, right, and obtain dF2 by dP2 and dF3 by dP3, and their value should be equal to lambda now, correct, and solving for lambda you will get 850 minus 600, that is what P2 plus P3 should be equal to, and replace for P2 and P3 and that is equal to 250, then you will get the lambda. Once you get the lambda, you can get what is the value of P2 and what is the value of P3, right? And that is coming out to be P2 is equal to 187.1 megawatt and P3 is equal to 62.9 megawatt. Now you again cross check, right? So dF1 by dP1 at P1 is equal to 600 comes out to be 8.016, and that is less than lambda, which is 8.576, and dF2 by dP2 is equal to, at P2 is equal to 187.1 should be equal to dF3 by dP3 at P3 is equal to 62.9, and that is 8.576, which is lambda, right? So all the constraints are met. P1 plus P2 plus P3 is equal to 850 megawatt, that constraint is met, and individual generator power output should be within their limits, thresholds, and that is met, and you are yet getting the most optimal combination of generator output, which is matching summation of generation is equal to load, total load, right? Now if you can cross check with the previous lambda, it was 8.626, that now you are getting lambda less than 8.626, which is 8.576. You got it? You will not get any other value lesser than this, considering all the constraints. Now let us go to the next level, where economic dispatch of thermal unit is considered with the losses, network losses. That means the same topology as I shown in the first slide. So total generation or need to also meet the transmission network losses, because in any practical power system there is a generation and there is a load. Generation is far away from the load demand, and there will be transmission line which is present in between, so because of which the line losses takes place. So, and we need to include the transmission network losses in order to make it more realistic. Let us say under some cases, for a given power output, if unit 1 has higher incremental cost compared to the unit 2, for economic dispatch the unit 2 is preferred over unit 1, right? Provided unit 1 and unit 2 are situated close by geographically. Let us say unit 1 and unit 2 they are situated close by. So if one of the generator is of higher cost, we will ignore that, we will try to extract minimum power from that generator and take maximum power from the second generator whose cost is less. But if the unit 1 and unit 2 are separated far away, then there will be a huge transmission loss, and transferring power from unit 2 including losses may not be economical. Let us say one generator is very cheap, the power output is very cheap, but it is situated far away, and if you transmit power you need to include the losses. So generation plus losses may not be economical as compared to taking power from that generator, which apparently little bit costlier, but total in considering the losses, this first generator output would be more economical, right? So the economic dispatch problem is slightly more complicated as compared to the case when there is no losses which is inculcated. So the constraint equation must include the network loss now. Now objective function Ft remains same as that of the case without losses. However, the constraint equation must be expanded as, now this is the total generation, sum of all generation should be equal to P load plus P loss, right? And what is your objective function? What is your constraint? That is P load plus P losses minus all generation should be equal to 0. So the Lagrangian function is L is equal to Ft plus Lagrangian multiplied by the constraint. In this just same approach, obtain partial differential equation dou L by dou Pi, and that comes out to be dou Fi by dou Pi minus lambda into 1 minus dou P loss by dou Pi. Earlier it was just dou Fi by dou Pi minus lambda without considering the loss. Now with inclusion of loss you will get this additional factor 1 minus dou P loss by dou Pi. So that means dou Fi by dou Pi plus lambda into dou P loss by dou Pi is equal to lambda. And solving you will get lambda is equal to dou F by dou Pi minus 1 by dou P loss by dou Pi, which can be further deduced as lambda is equal to penalty factor into dou Fi by dou Pi, right? And what is the penalty factor? This is 1 minus 1 by 1 minus dou P loss by dou Pi, where dou P loss by dou Pi is the incremental loss for bus I. That means there is a loss expression that you will see in the problem, and this loss expression is a function of all the generator, or could be of only one or two generators also, P1, P2, P3, right? Then to this function you obtain partial differential equation, dou P loss by dou P1, similarly dou P loss by dou P2 and dou P loss by dou P3, right? And then you will get penalty factor corresponding to each of the generator. So the minimum cost of operation is achieved when the incremental cost of each unit is multiplied with the penalty factor, which is same for all generating units in the same. Now earlier Lagrangian multiplier was not including any penalty factor. Now you need to include the penalty factor, that's it. When units are connected to the same bus, incremental change in transmission loss with change in generation is same for all the units, right? So hence all the penalty factors would be same. Therefore if penalty factors are same, then naturally their incremental cost will also be same. But if the generator buses are connected in different buses, then there will be difference in the penalty factor, and that is the reality, right? That is a reality, because so many generators are there. One is, let's say Ramagundam, you have a thermal power plant, and then you have a nuclear power plant in some other place, and hydro is in some other place. Then they have their own network losses, individual network losses, which are independent and different from each other. So the penalty factor is also different. The summary: above equations are collectively called as coordination equations. Solutions of economic load dispatch problem in the above case is a bit complex compared to the case without considering the network losses. There are two basic approaches. One is the use of network loss formula, and the other is the use of optimization tools incorporating power flow equations. Now the transmission network loss is a function of the impedances and the current flowing in the network, I square into Z, right? The currents can be further considered as functions of the input and load power, right? And it is more difficult to solve these set of equations. So what is the solution methodology? Step number 1, pick starting values for each generator that sum to the load, then calculate the incremental loss for each generator and the total loss also, which is P loss. The incremental losses and total losses will be considered constant until we return to step 2. First assume generation, total generation, and that is equal to load, then you obtain the incremental loss and total loss, find out them, and then calculate lambda that causes total generation to be equal to the constraint, load plus losses. Now the equation are again linear, we are just making it more linear so that we can solve it, and compare the generation from step 3 to the values used at the start of step 2. If there is no significant change in any one of the values, go to step 5, otherwise go back to step 2. So we will take an example to understand this. Again there are 3 characteristic curve, and the fuel cost is given, the oil price is also given, and there is a loss expression which is given in addition, right? And you can see the loss function is dependent upon individual generator output P1, P2 and P3. Now apply the coordination equation, find out dou F I by dou Pi, which is equal to lambda into 1 minus dou P loss by dou Pi for each of the generator, right? Then you will get these 3 functions, and there is a constraint which is total generation minus loss is equal to total demand, load demand. Now randomly you pick up P1, P2 and P3. values, right? P1 is equal to 400, P2 is equal to 300, P3 is equal to 150. 400 plus 300 is 700 plus 150 is equal to 850, that is equal to generation. Generation is equal to total generation is equal to total load. Now we do not know the loss, that's why we are just making generation is equal to load. Then we will slowly take another iteration and keep on doing the iteration, so that we will ultimately reach this obtain the solution where P1 plus P2 plus P3 minus P loss is equal to total demand. Now obtain the incremental loss. What is the incremental loss function? This is dou P1 by dou P loss by dou P1 is equal to 2 into the constant multiplied by P1. Similarly, obtain dou P loss by dou P2, dou P loss by dou P3. This you have got by obtaining partial differential equation of this function with respect to each generator, right? And then you will get these values. Then obtain what is the loss. How do you get what is the total loss? You see here, there is a loss function. You have assumed what is P1, P2, P3. Then you will get what is the total loss, right? And then now solve for lambda. Solve for lambda. To this expression you obtain the lambda, because you have got P1, you have got P2, you have got P3, and then obtain lambda from here. Then once you get the lambda, again obtain the generator values. Initially you assume something, then you find out the incremental loss, you find out the total loss, then find out the lambda. Then after you obtain the lambda, you apply to the same expression here. Then P1 is equal to 0.976 lambda by minus 7.92 divided by this constant. Similarly obtained for P2, P3. Then you would get a different values P1, P2, P3, because this is not yet converged. This will not converge also, because initially we have ignored the loss. We have made just generation, sum of the generation is equal to total load. Since these values for P1, P2, P3 are quite different from the starting values, we will return to step number 2. Now you consider this as the values for the next iteration and obtain lambda, and then again P1, P2, P3, the same procedure will follow. You obtain incremental loss for individual generator, then obtain the total losses, right? And then you step number 3 is the new incremental loss. Then you obtain the lambda, and then again you come back and find out what is the P1, P2, P3. Ultimately it will take 5 iterations in this problem to have a possible combination of P1, P2, P3, and the losses is also, you can see between iteration number 4 and iteration number 5 there is no much difference. It is almost getting converged. So even lambda, there is no significant difference, 9.5283 to 9.5284, right? So you can consider, you can keep on doing it to have even more accurate one, but the error is almost like 0.001 or something like that. You can converge. You can consider this to be the most optimal combination of the generators, which will make summation of generator is equal to total load plus, and that's it. This is the reference book. So in this week we have understood how, with the help of economic dispatch, considering economic dispatch problem, how by using Lagrangian multiplier approach we could solve for the first example, considering without losses, there is no loss, generation is equal to load, and first problem we have not even considered the inequality constraint. The second problem we have understood how we can solve by considering inequality constraint also along with the equality constraint. And then the third approach, where third example that we have took, where we have also considered the losses into place, we have find out the penalty factor, and we could able to obtain the suitable combination of generation which will make generation is equal to load plus losses. Thank you very much.